Most students think that interference is just the overlapping of two waves. But if the two waves will not be coherent, then these two waves cannot interfere, and you cannot observe a stable, observable interference pattern on screen. So, what is coherency of the two waves? We will understand it first. So, in this question, which where we will discuss the double slit interference pattern, and first of all, we will discuss what why the two sources need to be coherent. Okay. So, dear students, when we say the two waves are coherent, so basically it means that those two waves should have the same wavelength, obviously same frequency. But the third one is very important, right? Which is usually you will see whenever you will read the textbook. It is said that it should have the two sources must have a constant phase difference. So before we answer the first question, I will explain you how the two waves can have a constant phase difference, and then they can interfere constructively or destructively. So, for example, this is a one wave source, right? So, this is a one wave, right? And with what another wave, it will interfere specifically. So, here I am going to show you another wave, exactly this one. So, right now, you see that there is a no phase difference between them, and there's a constant phase difference. Right now, the phase difference between them is 0 degrees. It will remain 0 degrees wherever you go throughout the wave. Okay, but let's say if I place this wave forward or backward, so students, now you see if I take the 2 points, for instance, these 2 points, so what is a phase difference between them? It not pi over 2? It's a constant phase difference. If it will remain constant throughout the wave, let us take any other 2 points, okay? So, because we claim that there must be the constant phase difference, right? So, you see that there is here again the phase difference is what? Pi over 2. Because any two waves which have a constant phase difference, let's say the pi over 2, there is a one thing that from which you can identify that at this point where this is giving you zero value, the other wave is giving you the maximum value, right? So this is called the constant phase difference, same wavelength and same frequency. If this happens, the two waves can interfere. So students, constant phase difference, or you can say in phase, and any two waves will be in phase if they have the constant phase difference or 0, 2 pi, 4 pi, right, 6 pi, right? If these are the phase differences, we can say those two waves are in phase. Okay, and only coherent light can produce this pattern. Okay, so in this diagram, the double slit interference pattern, we see that what they are saying that the 2 points p1 and p2 are the points of destructive interference. Okay, so it means that these are the dark fringes. Okay, these 2 points, and the angle between them is phi. Okay, and the wavelength is 720 nanometer, right? And this is 0.12 millimeter, which you know is this distance, right? So first of all, I will show you how the two waves, how the these two monochromatic light interfere after passing through the two slits. So let's say this is a light that is going to fall on the two slits, and the distance between any two consecutive wavefront is always, is the lambda. All right. And this is the distance between the two consecutive slit, which is the D. Okay. We represent it with the letter D. So what will happen when this light will pass through this? Because both the light passing from both slits is the same wavelength of light, so they are eligible to do interference. So this light will diffract, as you see, and as a result the light will diffract from a other slit as well. And when these two lights will meet with one another, at some points they will do constructive interference, and other points they will do destructive interference. And this all depends on their path difference. Dear students, you know it very well that if the path difference is integral multiple of wavelength, then it will be a constructive interference, and as a result, they will make a bright spot. Okay, so just like on the screen, you see that at a center there is always a constructive interference because the two lights which reach at the center from the two slits does not have any path difference, so they will interfere constructively. All right, so you will have all the bright spots formed on the screen at a fixed positions. Okay, so according to our questions, you see that the P1 and the P2 are the dark fringes. Okay, so it means that must represent by this is P1 and this is P2. Okay, and the distance between them, you should remember the distance between the two consecutive dark fringes is always, what do we call it, fringe spacing. So dear students, it means that this distance is of course the fringe spacing, which is s is equals to lambda d over small d. Whereas you know the capital D is the distance between the slits and the screen. Okay. Now, if we go back to this diagram, right, can I say the distance between this and this one is lambda d over small d. Okay. All right. So now I am going to draw the geometrical diagram from which we will do the derivation and we will find out the answers. So students, you see, we are getting a right angle triangle. If I just show you this one, right? Okay. So this is it not? This is a half angle, phi over two, right? And this is a point P1, right? Which is your destructive interference point. Okay, it's a dark fringe that we call it. Okay, and I had already shown you the distance between the P1 and P2 is the fringe spacing. All right, so it means that the distance from the this point to the middle, right, to the center where we have always a bright fringe, is it not s over 2, right? Is it not the lambda d over 2t? All right, so I'm trying to show you this is a right angle triangle. Okay, angle is given, opposite side is given, that is lambda d over 2d. Okay, and this is our method one, remember, whereas the adjacent side is d. Okay, we don't need this thing, but I'm just mentioning it here. So in this right angle triangle OMP1, OMP1, right? What we can say, if I take a tan of the angle, right, that is phi over 2, tan phi over 2, it should be equals to the opposite over adjacent, right? So opposite is s over 2, right? And adjacent is d. So tan phi over 2 is equals to lambda d over 2d divided by this d, the distance between slit and screen. Okay, so in the next step, you see that we can write it like this: 2d and this big letter d, right? And the phi is the angle you see in the diagram. And in this question, the first question we sorry, yeah, in this one we have to find out basically this phi angle. All right. So what we get, this d and this d is cancelled out, right? And the tan phi over 2 is equals to lambda over 2d. Now, look, if the angle is very small, because this angle is so small, and in the radians, if you calculate, if you take the tan of a small angle in radians, it will be equals to angle, right? So that should be, we should write like this. Okay. So it means that now phi will be equals to lambda over 2d times 2. So it should be lambda over d is 6 multiplied by 10 to the power negative 3 radians. So this is the angle. All right. Now I'm going to show you the another method, right? If it's good if you understand another method, right? Because we know that the point P1 is the destructive interference point. It is a dark fringe. Okay. So it means that we can also solve it from the method of finding the path difference between the two waves. Which two waves? The one wave that is reaching at this point, okay, and the other wave that is reaching at this point, okay, at the same point. So basically the path difference between these two should be lambda over 2, because this is the first dark fringe, This is the first dark fringe after the central maximum. So the power difference for destructive interference always starts from lambda over 2. So students, now this time I'm just showing you the point P1 here, right? Okay, so what pattern will be formed, right? So just imagine the one wave that is going from the one slit. Okay, I'm going to draw the ray of light. Okay, this is a one ray of light, and this is another ray of light that has traveled from the second slit to this point. Okay, so obviously you can see that both are not traveling the equal distances, right? So which one is traveling more distance? In order to find it, we will draw a perpendicular line as we always do, right? From the one ray of light to the another ray of light. Okay, so okay, so exactly like this, right? So what you see? Okay, now see again, right? You see that I am dropping a dotted perpendicular line from the ray 1, on the ray 2. Okay, so you can easily see that what is the additional path covered by the ray 2. Okay, all right, dear students, so it is the d, distance d. This is the angle phi, right? The same angle. Okay, and this is always the d sine angle. So this should be phi over 2. Okay, why I'm saying it should be phi over 2? Because if you remember this diagram that we have drawn it before, right? Okay, you see clearly that what is the angle? Phi over 2. So the same angle will be formed in that triangle, right? You can prove it geometrically, but it's not needed right now. So students, in our math 2, right, which we are doing right now, d sine phi over 2 is equals to, this part difference is equals to lambda over 2, 3 lambda over 2, or 5 lambda over 2. Which one? It is obviously lambda over 2. And why it is lambda over 2? Because this is the first destructive interference, right? First dark fringe. Okay, if it would be the second dark fringe, then it will be 3 lambda over 2. All right, so you can find from here sine phi over 2 is equals to lambda over 2d. Once again, sine and tan are both gives the same value as of angle, right? So it will be phi over 2 because angle is very small. That's why it is equals to lambda over 2d. So dear students, you see that we are getting the same result, lambda over d, right? So just like we got here, right? So it means that we will find out the same result, that is 6.0 times, yep, 6.0 times 10 to the power negative 3 radian, right? This is the angle. Okay, I hope these two methods are enough. Now suggest how now I'm going to the third question. Suggest how energy conservation is consistent with the fact that energy at P1 and P2 is 0. Okay, now you know that the law of conservation of energy cannot be violated. So how does this is manifested in this question, right? How it happens in this double slit experiment? Okay, so all the energy that falls on the two slits, right? I have shown you this light have certain energy, right? So this energy is conserved, right? First of all, it passes through the slits. Okay, so the energy that finally falls on a screen, that energy is distributed uniformly. It is concentrated on the maximas, right? You can call them maximas, right? Whereas what happens at the dark fringes, right? So if I show you here, give me a second, dear students. If I show you, let's say this is a one wave, right? Coming from the one slit, right? Now this is another wave coming from the another slit, right? So what happened at this point B? The crust meets with trough, and trough meets with crust, right? Because they have power differences lambda over 2 and 3 lambda over 2 of so on. So what happens finally? The two waves cancel out each other's energy, and all the energies are concentrated on the maximas. All right, on bright spots, which we can say maximas. So energy missing is found at maxima. All right, and why it's maxima I had explained you in detail. Okay, Now the next question is about the diffraction grating, and that is not included for the standard level, those students who are taking SL, right? So for example, a beam of light that we are falling have the wavelength in this range, 550 nanometer to 650 nanometer. So you can say from the green light to the red light. Okay, from the green light, it means that all the lights below 550 nanometer, okay, blue light or violet, indigo, those are missing in this wavelength range. Okay, now it is incident normally, right? So it means that the angle is 90. So when we will apply the formula for the diffraction grating, we will use this angle to find the maximum order of diffraction. All right, now grating has the 580 lines per millimeter. Now it tells us that in the length of 1 millimeter there are 580 slits, all right, which shows us that how small is the size of a single slit, which I can obviously cannot draw on the on this blackboard. Okay, but I will show you a diagram. Okay, now outline why the interference at M is constructive. Once again, yes students, you can connect the dots, right? When the interference is constructive, right? when the path difference when the path difference is any one of them, right? 0, lambda, 2 lambda, 3 lambda, up to so on. In simple words, it is the integral multiple of the wavelength, okay? Because only in that case, the two waves meet up in such a way crust fall on crust and trough falls on trough, all right? So that's why. But at M, all right, at M, why it is constructive? Because all the lights which are reaching at M are, let me show you. So students, this point is M. All right. Now the question is why there is always a constructive. So the reason is same. For example, now I have to show you because light is falling on this whole diffraction grating. So the light that is coming from this slit and which is reaching at the point M. All right, like this light. Okay, and 1, 2, 3, 4. The light that is coming from this slit, these two light rays, okay, these two waves are traveling the same distance. All right, so I'm talking about specifically this one, right? Wave 1 and 2. In the same manner, the light that is coming from this slit is traveling the same distance as the light traveling from this slit. Okay, so don't you think that there is always a phase difference 0, or sorry, there is always a path difference 0 between the two rays of light, okay, which are coming from the same distance, from opposite of this fraction of opposite of this screen. Okay, so when there's a power difference is 0, and moreover when all the lights are reaching at this point M, so they will add up into each other. So that's why there is always a constructive interference. And you can see wave arrive in a phase and the power difference is 0. All right, and why the power difference is 0? Because the distance traveled by the two waves is same. Okay, now the next question is, and which is the last question, determine the largest order of diffraction pattern in which all wavelengths in incident beams are present. Now dear students, before we go to this question, you must your idea should be clear that when this light, okay, which was basically the composition of all the wavelength, so I'm talking about this light, okay, so it carries the wavelength from 550 nanometer to 650 nanometer. All right, this beam of light, okay, when this light will fall from the diffraction grating, this light will split, okay, and as a result, on the screen you will have a central maxima, and from above the central maxima and below the central maxima we will have orders: first order, second order, maybe the third order. In every order we will have all the wavelengths in this range. Okay, there are large number of wavelengths: 550 nanometer, 551 nanometer, 552 nanometer, right? So you can imagine that we have a large number of wavelengths. Okay, so what is the largest order, right? For this, if you want to know, let's go back to the equation of the diffraction grating, which is d sine theta is equals to n lambda. All right. Now, in order to get the largest order, right, d sine theta over lambda, right? Theta should be 90. And wait a second, what is a d? D is equals to the L over n, basically, right? It is equals to 1 millimeter. It is basically a size of a slit, all right? 1 millimeter over the 580 probably, right? So it will be a very small number, which is 10 to the power negative 3 meter over 580. So students, if I use this value, 10 raised to power negative 3 times sine 90, okay, because we want to find the maximum order, and this said in a start that light is falling normally, divided by 580, okay, multiply by, now the selection of wavelength is very crucial here, and I will explain you with the help of diagram why it is important. Now notice that I'm using the wavelength 650 nanometer, right? Times 10 to the power negative 9. Okay, and why I have selected this one? Not because the mark scheme says that you should use this value. I will explain you why it is. Okay, so if we find its value, right, n is equals to, so we get 2.65. Right, now understanding the meaning of 2.65 is very crucial. It means that, dear students, the screen, okay, grating, diffraction grating screen contains, I would say, two complete orders, right? When I say two complete orders, means it contains all the wavelengths from 550 nanometer to 650 nanometer, right? Let me show you, okay? And the third order is not fully completed, because if you see, it is 2 plus 0.65. It means that the third order is just, you can say, 65% is on the screen, and 35% of that order is missing. Okay, let me show you on the screen. So students, I'm not showing you at the center any specific color, because in simple words, it is basically a mixture at a center, right? Mixture of all wavelengths. All right. So for us, the other orders are important. So the first order, as you know, that it is starting from the green to red. Okay, green to red. Understand? So how many colors do you have from green to red? Okay, whip wire. So green, yellow, orange, and red. Okay, so first of all, we will draw the less wavelength. Okay, which is obviously green. Okay, so look at this. Okay, I'm right now drawing the first order. Okay, and then we will have yellow, and then we will have orange. Okay, and then we will have red. So dear students, this is a one complete order. So this is a second complete order, right? Since you remember we got 2.65, so it means that in a next order we will have just imagine, let's say, the two colors only, right? Okay, and remember that the more the wavelength, the light that have a larger wavelength will be always relatively away from the center. All right, so you see that we have a red here and we have a green here. Green is close to the center, okay, because you can see from this formula d sine theta is equals to n lambda, right? So theta, sine theta is proportional to lambda. So if the wavelength is small, angle will be small. All right, so this is another information. So students, just the last thing, you see I have shown you the two complete orders on the other side of the center also, because the order that we get, actually this is equals to plus minus 2.65. All right, so the positive you can express them above, and negative you can show them on the other side. Okay, so that's why we should select the wavelength 650 nanometer to find out the maximum order. So the same answer you see here, n is equals to 2, and I hope this extra explanation was helpful for you, okay, and subscribe this channel. Thank you so much for watching.